This is the B&K 1477. It's a 15 megahertz scope and dual trace. Measures everything time-base wise from a half a second to 0.5 microseconds, and it does it in 19 steps with a 20th step to give you the XY capability where channel B controls the horizontal sweep and channel A shows you the vertical. Anyway, we have on the screen right now a signal roughly 2 kilohertz, 2.5 kilohertz. You can see the waveform there, but well, let's see. Is that one waveform? Oh no, it's really two waveforms. Perfectly in time. The image is razor sharp. There's plenty of intensity left. I can swing this intensity way up, or I can take it way back. We are right now setting it about 50%. Let's take it through some tests. Okay, we have both probes connected to the calibration point on the oscilloscope. We get 1 volt peak-to-peak provided to the input channels. Right now we're looking at channel A, and we're at 0.2 volts per division. So 0.2, 0.4, and then a half would be 0.5 volts positive, 0.5 volts negative, 1 volt peak to peak. And if we change to 0.5 volts per division, we're up 1 division, down 1 division, 0.5 up, 0.5 down, 1 volt peak to peak. Now we're at 1 volt per division, and we get a half volt up, half a division up, half volt up, half a division down, half volt down, 1 volt peak to peak. So that was channel A. Here's channel B. We'll start again. 0.2, 0.2, 0.4, 0.5 up, 0.5 down. And there's your 0.5 up, 0.5 down, 0.5 up, 0.5. There's a half a division up, half a division down. So that's at 1 volt per centimeter per division. So both channels are tracking. And let's move on. Okay, let's take a look at the time base. Right now, our time base is set for 1 millisecond per division. And we are right now showing a trace that has a cycle completed in 2 divisions. So that's 1 cycle in 2 milliseconds. That means we must be working at about 500 cycles a second, because if it was 1 cycle in 1 millisecond, that's 1,000 cycles per second. If we're doing it in 2, we have to divide by 2, that'd be 500. And yes, we are running at 500 and measuring 502. So if we change now to 0.1 milliseconds per division, I'm sorry, that's 0.2 milliseconds per division, and we're getting 1 cycle in 10 divisions. So we're getting 1 cycle in 2 milliseconds, so that's 500 cycles a second. All right, let's try increasing the frequency. Right now, we can see that we have a full cycle in 1 division. And we are set at 1 microsecond. So if we have 1 microsecond per division and we got a full cycle, we must be going 1 megahertz. And right now, we're reading about 1 megahertz, 1000 kilohertz, so that's 1 megahertz. So we are agreeing with our time base to 1 megahertz. Let's try kicking it up one more. I'm now getting 10 full cycles in 2 divisions, and that's at a reading of 0.5 microseconds per division. So 1 microsecond in 2 divisions. I've got 10 full cycles in 2 divisions, so I've got 10 full cycles in 1 microsecond. So I must be running 10 megahertz. And in fact, I am running 10,000 kilohertz, which is 10 megahertz. Okay, it's kind of difficult to hold this stable for you right now. We're looking at a sweep from an RF sweep generator that's running from 0 to roughly a megahertz. And as you can see on the left, you've got a lower frequency wave, and then it's oscillating faster and faster till it gets to the right, and it's very compressed. I'll change the scale so that we expand it a little bit. And what I'm going to do is I have a little device here, and this device is called a ceramic filter resonator. And that resonator resonates at 455 kilohertz, which is the IF frequency used in a great many communications receivers for the IF stage. And we're gonna see what happens on the screen here as we sweep through that signal. So as we increase in frequency and we approach the 455 kilocycles, we see things stay stable, and then suddenly we see this resonance point where the voltage grows and spikes. And we get a sudden drop off, and then we're flat again going off to the right. That's the characteristic of the 455 kilocycle resonator that makes it unique. The fact that it resonates at this frequency means that it has a higher impedance at this frequency, that it uses less power, and you'll see the voltage spike up here. If I was to sweep through more slowly, you'd see that spike more pronounced. It would grow. I'll do that right now. We'll drop the speed of the scan down, and you'll see the spike grow. And if I increase it, you'll see the spike decrease. And the reason for that is that the scope can't display the image fast enough. It's being swept through so fast that for the very sharp spiky peaks, the electron beam is hitting the phosphor, isn't hitting it even long enough for it to be able to display it. So as I slow it down, like I say, you get more of a peak. This is one of the exciting things that you could do with this scope, is to study the transfer characteristics of parts like this, of circuits, filter circuits, and so on. So, again, whoever gets this is going to be a happy person. Good luck. I'm also including a service manual for the scope, which takes you through calibrations, operation of the unit, adjustments, and most importantly, in my mind, I have parts lists, schematic diagrams, and they're both an 8.5 by 11, and I also have them on 11 by 17 for easy viewing. Here's power supply board layout, vertical amplifier, sweep board, schematic for the unit, and so on. So you'll have a good service manual to help keep this thing up.